Hello. Okay, Dr. Bhaskar.
Hello.
Yeah, I think you should start.
Okay, ma'am. Thank you.
Okay. Yeah. Okay.
Good morning, everyone. So, I'm Dr. Bhaskar, NMR in charge at IIT Madras. I have 15 years of experience in this field. Okay. So, first of all, I would like to thank Professor Sanjay Kumar for introducing me to Professor Ranganathan, who provided this wonderful opportunity. And also, I would like to express my special thanks to Dr. Vidhi Chaudhary for her smooth coordination of this meeting. Now I am moving on to the presentation.
सुनो
My screen is visible.
Yes. Yes.
Okay. Okay. Thank you. Can I start?
Yeah, you can start.
Thank you. So, good morning again. Good morning, everyone. So today I'm going to discuss about the instrumentation and working principle of NMR spectroscopy. Before going to the instrumentation part, why we need NMR? Okay, then only you people will be interested to listen these things, because many people are thinking NMR is only for organic people. It's not like that. It is common for all the people. NMR is a very vast field. Okay, so it will give the NMR will give the information about the structural information of organic compounds and proteins and nucleic acids analysis we can do using the NVOE and ROSI experiments. Okay. And dynamic studies we can do the ring barrier energy. Those are the things we can calculate through the dynamic NMR, and also reaction kinetics we can monitor through the NMR. Using the Eyring equation we can find out the delta G also. Okay. Then metabolomics, we can find out the metabolomics and metabolite profiling with the help of NMR, and qualitative quality control in pharmaceuticals. What are the impurities are there, impurity profiling. Those are the things we can do through the NMR. In material science, in generally material science people are, NMR is not related with us. And they're thinking like that, but it's not like that. In material science, NMR will be most useful. We can find out the material characterization and polymers characterization we can do using the diffusion experiments. We can find out the diffusion coefficient of polymers, and homonuclear decoupling method will give the segmental mobility of polymers, and with the help of homonuclear decoupling we can find out the glass transition also, polymers glass transition. And if it is a copolymer, we can find out the polymeric ratio also. With the help of NMR we can find out the monomeric ratio. Okay, so in food industries we can find out the food adulteration. What are the adulterations are there? Those are the things we can find out through NMR. Nowadays the honey profiler is the most important thing. So in honey it is what is the purity, what are the impurities are there, those are the things we can find out the with the help of NMR. And forensic science, NMR is the most useful. And materials magnetic property also, magnetic susceptibility we can find out through the NMR using the Evans method. So we can find out the magnetic susceptibility of materials. And relaxation measurements, T1 T2 relaxation also we can find out through the NMR. And diffusion measurements, polymers molecular weight also we can find out through the NMR. Using the Stokes equation we can find out the polymers molecular weight and polymeric molecular structure and molecular radius. Everything we can find out through the Stokes equation. Okay, so next I'm moving on to the instrumentation part. Okay, so NMR has the three major components. One is the superconducting magnet, second one is the console, the third one is the user interface. This is the complete picture of NMR instrument. First, I'm going to talk about the magnet, NMR magnet. The magnetic components are most important part of the NMR spectrometer. Generally, magnetic materials are produced magnetic field for the NMR instruments. Two kind of magnets are available. One is the permanent magnet. The next one is the electromagnet. In the olden days, permanent magnets were used. That is the very lower frequency. The maximum field strength is 1.5 Tesla. Nowadays, the superconducting magnets are used. Once the superconducting magnets are developed, the NMR has evolved a lot of things. The magnetic field strength is 6 to 23.5, around 24 Tesla. The superconducting magnets are produced. The superconducting magnet is a type of electromagnet. In coils, these coils are made up of superconducting wire. Some materials are cooled to lower temperature, around 4.1 Kelvin. It lost all the electrical resistance. It acts as a superconductor. This property is called the superconducting property. In generally, two type of superconductors are available. One is the type 1 and another one is the type 2. Pure metals exhibit zero electrical resistivity at lower temperature. These materials are called the type 1 superconductor or soft superconductor. Alloys exhibit zero electrical resistance at lower temperature. These materials are called type 2 superconductor or hard superconductors. In generally, for NMR purpose, type 2 superconductors are used because it has a lot of thermal stability and mechanical stability also. In generally, for NMR purpose, niobium titanium and niobium tantalum titanium tin alloys are used. Up to 12 Tesla, generally people are using niobium titanium alloy. So it is a more mechanical stability. So, but it will generate maximum 12 Tesla. About 12 Tesla, people are using niobium tin alloy. So it has some actually lower mechanical stability. So that's why if you are going for above 500 megahertz, the cost will be more because the niobium tin alloy making wire is a very difficult. So that's why the above 500, if you are going, the cost will be more. This is the actually schematic diagram of superconducting magnet. So actually, this is the matrix, copper matrix. These niobium titanium coils are binding. These are the niobium titanium coils. The copper is giving the strength of the coil and carrying the current to the superconducting wire. This is the complete winding of the superconductor. The coil of wire is kept at temperature at 4.2 Kelvin or less. By immersing into the liquid helium, it acts as a superconducting magnet. As long as current flow is available in the coil, the superconductivity will be stayed. Once the current is caused to flow the coil, it will continue to flow for as long as coil kept in the liquid helium temperature. Small electrical loss will occur over the time due to the resistance of the coil. This loss in the order of ppm per year. So we don't mind those things. The NMR magnet has three compartments. The first one is the liquid helium chamber. Actually, this is the.
I have one question here.
Yeah, sure, ma'am.
Yeah, actually, here we have in SAIF IIT Patna, we have Geol make NMR, 500 megahertz NMR, and
Okay,
it's in this machine we use helium twice in a year.
Okay, ma'am.
So up to what percent we are safe? What percentage of the level we are safe?
Actually, that is depending on the magnet, ma'am.
Okay.
Yeah,
because
so
here in
minimum
engineer say,
some of the
yeah.
maximum 30% is the safe level, ma'am. 50 when
Okay.
percentage is helium reach the 50%. So at least we have to remind the people because some transport delay, those other things will be there. At the 50% it reached, we have to inform to the engineers.
Engineer. Okay.
Yes, ma'am.
So up to 30% we can.
Yeah, we can survive.
Yeah. Okay.
Once it quenched, that re-energizing cost will be more, ma'am, because when
Yeah,
we are
yeah, yeah.
re-energizing,
That's why I'm asking.
yeah, lot
Yeah.
of heat will generate. So that time we have to fill the helium. Nowadays, the helium cost will be more.
Because nowadays, right now our machine is under warranty, but after warranty we should careful, no?
Yes, ma'am. And
Yes.
also
Yeah.
that liquid
Yeah.
nitrogen filling is most important, ma'am. How you are maintaining
Yeah.
the liquid nitrogen level,
Yeah.
based on that, the liquid helium
Liquid
time will
helium.
increase, ma'am.
Yeah, yeah. So another question related to the liquid nitrogen.
Yes, ma'am.
In our general practice, we fill the liquid nitrogen when it comes 50% level almost.
That is
Yeah.
actually that helium evaporation will be more, ma'am. So at
Okay.
least
So
weekly once try to fill, ma'am.
okay.
Yeah.
Nee, we are weekly filled, but our level reached up to 50%.
No, ma'am. No, no. Don't wait for 50%,
Okay, okay.
because
Because
in surrounding
yeah, in our
little.
general practice, we are filled weekly.
Yes, ma'am.
Yeah. Okay. Thank you.
Yeah. Okay, ma'am.
Mm,
Is it better
mm.
actually weekly once if you are filling? It will be.
Yeah.
Do you have a liquid helium? Sorry, liquid nitrogen plant, ma'am?
No, no. Actually, we
Oh,
buy
okay. That's
from.
a difficult.
Yeah, it's very difficult for us because
Yes,
we
yes.
buy it from Patna.
Oh,
Yeah,
okay,
it is
okay,
away
okay,
from
okay.
40, 35, 40 kilometers away from SF,
I
IT
understand.
Patna. Yeah,
But
yeah.
that helium, because of that liquid nitrogen, how we are maintaining that helium stays longer time.
Yeah.
Yes,
Okay.
ma'am. Okay,
Thank you.
okay, ma'am.
Okay, go
Thank
ahead.
you. Yeah, the NMR magnet has the three compartment. The inner one is the liquid helium chamber. Okay, so actually this is the liquid helium chamber. These are the superconducting coil. The inner one is the thermal shielding. This is the thermally shielding, not magnetically shielding. Okay, so many people are thinking the NMR is liquid nitrogen and liquid helium. We are doing at that temperature. No, we are doing measurement at room temperature. If we want, we can increase the temperature. Otherwise, we can decrease the temperature. Otherwise, we are doing all the measurements in room temperature. This is the inner shield. This is the one inner shield. Okay, so after that, the first one is the inner shield. The next one is the shim, RT, room temperature shim. Then this is the superconducting coil, and after that, this is the outer shim coils, and this is the outer vacuum, and this is the casting, and this is the liquid helium fill-in port. Okay. So the first one is the liquid nitrogen chamber. After that, vacuum. Then next one is the liquid nitrogen chamber. Okay, so the liquid nitrogen, why we are filling? So we cannot stop the helium evaporation, since helium is the very expensive. We can reduce the helium evaporation. That is the reason we are filling in the liquid nitrogen in the third compartment. How we are maintaining the liquid nitrogen? That liquid helium will stay. This is the schematic diagram of NMR magnet. Okay, so these are the nitrogen fill-in port, and this is the helium fill-in port, and this is the bore actually. Two kind of bores are there. One is the wide bore and another one is the narrow bore. This wide bore, the helium evaporation will be more. That is suitable for solid state NMR experiments. But the narrow bore is suitable for regular routine experiments. Okay, so here only we are inserting the probe. So this is the superconducting coil, and this is the helium, and the next one is the liquid nitrogen, liquid helium and liquid nitrogen. These are the vacuum chamber. Here only we are inserting the sample. Once we insert the sample here, directly it will, with the airflow, it will float and it will reach the probe here. Here only we have connected the probe. Okay, so these are the nitrogen towers. This is the bore actually. Already I told two kind of bores are there. One is the standard bore or narrow bore, and another is the wide bore. So it's depending on the probe. What are the experiments? Depending on our requirement, we can buy. In generally, the wide bore, the liquid helium evaporation will be more. We have to fill at least once in 3 months. This is the cutoff of the superconducting magnet. This is the coil, and this is the liquid helium chamber, and next one is the vacuum. The last one is the liquid nitrogen. Okay, so the NMR magnets are containing the liquid nitrogen and liquid helium level sensors. We can see the liquid nitrogen level, liquid helium level, and with the in the computer itself, we can see all the things and all. The NMR magnet is thermally shielded out of the magnetic field. Here also thermal shield will be there, and magnetic shield also will be there. The same magnetic material. What are the magnetic niobium, titanium, or niobium tin? These are the alloys. Again, they kept here for magnetic field shielding. Recently, all the magnets are completely shielded, so that's why we are safe. The NMR sample probe and shim coils are located within this borehole. Already I told the vertical bore, actually two kind of bores are there. One is the wide bore, that is the 89 mm, and next one is the standard bore, that is the 51 mm. This wide bore is suitable for solid state and imaging probes. This narrow bore is suitable for regular solution experiments. Sets of superconducting shim coils embedded within the cryostat. Actually, this is the superconducting coil, and addition to that, here shim coils are there. I'll explain later on what is shimming and all. Okay, this some of the shim coils are present in this liquid helium itself. That is called the cryoshims. It will make the homogeneous magnetic field in the sample area. Okay. So this is the superconducting coil here, and magnet shims are here, and this is the probe and gradient. This is the radio frequency coil, and top of the radio frequency coil we can see the gradient coils. The radio frequency coils are close to your sample. These are the shims are room temperature shims. These are the things present in the magnetic bore. One is the cryoshim, that is present in the liquid nitrogen, I mean liquid helium itself, in cryogen itself, and another one is the room temperature shims, that is present in the bore, inside of the bore. The innermost structure is the radio frequency coil. Superconducting magnet. Actually, these are the complete structure of superconducting magnet. What are the safety measures we have to do for NMR? 1 minute, ma'am. Sorry, ma'am. Actually, outside some noise came.
No.
Can I continue?
Okay. Yeah.
Yeah. Sorry, because outside some drilling works are doing. People are doing.
Okay. No problem. Go ahead.
Yeah. So these are the safety measures we have to follow for NMR magnets. In NMR magnets, always live. We cannot switch on and we cannot switch off. It is always once re-energized means that's all. So once quenched, again we re-energizing it cost will be very high. So we have to maintain the helium and liquid nitrogen level. Okay, so that cryogen filling is most important. If we fails, that magnet will quench. So we are in trouble. Okay. So no ferromagnetic or magnetic materials are allowed inside the NMR room. Since it's a shielded, so small leakage will be there. Up to 2 meters, we can feel the 50 Gauss magnetic field. So it's depending on the magnet. In generally, the 50 Gauss we can feel up to 1 meter. So some leakage is there, it will be more. So that's why we should not keep any magnetic material inside the NMR room. No watches, no cell phones, no iPads, nothing is allowed. Okay, inside the magnet NMR room. So credit card or ATM card, if you are bringing to the near to the magnet, next day onwards, your ATM card will not work. If somebody is having pacemaker or bone implant, so those people also not allowed near to the magnet. Next, I am moving on to the probe. Actually, probe always we are connecting in down of the superconducting magnet in the bore. Okay, the probe accepts the sample, send the radio frequency energy to the sample, and detects the signal and emerging detect the signal from the sample and send it to the IPSO. Okay. The probe consists of radio frequency coil, sample spinner, temperature controlling circuit, and gradient coils. The probes placed in the center of the magnetic field, bore. The probes are constructed with two radio frequency observed coils. One is the close to the sample, that is the inner coil, and second one is the outer of the, next to the inner coil, that is the outer coil. These two radio frequency coils are surrounded the sample. Here in image we can see this is the inner radio frequency coil, and next one is the outer radio frequency coil. This is the NMR tube. This is the spinners. These are the gradients. It will support for shimming. Here in down we can see the tuning rods and all. Radio frequency tuning rods. These coils are allows respond to multiple frequencies and to allow the excitation or irradiation of the multiple nuclei. The nuclei that use the inner coil are detected with the highest sensitivity than the outer coil, because the inner coil is close to your sample. It has the higher sensitivity than the outer coil. In the broadband observed probe, constructed with the inner coil tuned for the broadband nucleus, X nucleus, other than proton. It will give the maximum sensitivity of other than proton nucleus. For example, C13 or P31 and all. So these are the probes are suitable for normal, organic people and small, who are the people working in organic chemistry, small molecules, and regular experiments. Next one is the inverse probe, the broadband inverse probe or indirect detection probe. In this probe, the inner coil is constructed with the hydrogen nucleus. It is the hydrogen nucleus is the inner coil is more sensitive generally because it is close to your sample. In this inverse probe, this inner coil is the hydrogen and outer coil is the X nucleus. Okay, so these are the probes are suitable for biomolecules. Who are the people working in the natural products, biomolecules? Then who are the people need high resolution proton NMR spectroscopy? Those people, this broadband inverse probe is suitable. In general users, broadband BBO probe is suitable. This temperature range we can do -150 to +180 degree. So for -150 we can use the liquid nitrogen and we can reach up to -150 degree. And high temperature with the gas itself inside a thermal heater are available. This will heat our sample and increase the sample temperature. The third one is the nowadays actually these cryo probes are very expensive, but they introduced the cryo or cold probe technology has made significant advantage in the probe technology, because this probe coils built in the preamplifier, all the electronics and all cooled with the liquid helium. It will increase the sensitivity. So this 4 times it will increase the signal intensity. When we have a small amount of compound, the cryo probes will more help. Who are the people working in natural products and all, these cryo probes will help, but it is a very expensive. So the maintenance itself, we have to spend a lot of money.
Here I have one question.
Sorry, ma'am.
Yeah, here I have one question. If a machine have a cryo probe, then only we can use only cryo probe, na? There is no
no option, ma'am. Because
no option, na? Because it is embedded in the liquid helium, na? So that's why we are not able to change the probe.
Yes, ma'am.
Okay.
Yes, ma'am. For that maintenance itself, I inquired this broker. They told per year 25 to 30 lakhs for only probe maintenance.
Okay.
Yeah. So
okay. As a general query, in IIT Madras, it is available or in somewhere?
No, ma'am, we don't have, ma'am. Only the few institutes are having this cryo probes and all.
Okay.
IISc have, PAFR have.
Okay.
Yes. Okay. Because the maintenance is very expensive.
Yeah, because due to the liquid helium.
Yes, ma'am.
Also.
And next one is the ProDigi probe. Nowadays they have developed. This maintenance is little bit cheaper compared to the cryo probe, but still the maintenance is expensive. This is instead of liquid helium, they are using the liquid nitrogen. It will increase the sensitivity, signal intensity 2.7 times. That is the ProDigi probe. So this is first, now I have completed the NMR magnetic part and probe part. Next, I'm moving on to the console. This is the console. So these are the receivers, and here the signal generator or synthesizer. Generally, NMR people used to call synthesizer. This is the pulse streaming organizer, and Bruker generally used to call IPSO, intelligent pulse sequence organizer. And this is the shim boards. So gradients and all here. So this is the generally in Bruker BSMS, they used to call BSMS. It will help for inject the sample, insert the sample, and eject the sample, spinning the sample. Those are the things it will check. And this is for completely solid state. The radio frequency controllers and amplifiers are available in this NMR cabinet. Okay, so the complete radio frequency controlling unit generate the radio frequency pulses used to excite the sample and receive and amplify, digitalize the signals and emitted by the sample. In radio frequency channel, generally three coils are available. One is the observed channel, and another one is the lock channel, that is for deuterium coil, and third one is the decoupling channel. In general, this is for two channel instruments. If we have a three channel, one is for proton and another two is for X nucleus. These two channel instruments, maximum we can do the 2D experiments. Next one is the amplifiers. The amplifier, also known as transmitters, signals of relatively large amplitude and required to excite the NMR sample, and hence the need for amplifier. The two main amplifiers are, one is the selective amplifier. This is for proton. Only in this amplifier will give the only proton frequency, or maximum frequency for fluorine also. These two frequency it will generate. Another one is the X nucleus broadband amplifier. It will cover remaining all the nucleus. The pre-amplifiers used to amplify the signals. What are the signals we have received? It will amplify and it will send it to the computer. Next one is the user interface. It's a computer. So what are the signals we have received from the pulse streaming organizer? It will transfer into the computer. So what are the commands we are giving into the computer? It will take into the instrument and it will do the one by one. That is the what that pulse streaming organizer is doing. It is also placed in the console. Okay, so now instrumentation part is over. Can I move on to the working principle?
Yes.
Okay, so principle of NMR experiments. Any NMR active nuclei present in the strong magnetic field, the nuclear energy level will be splitting. That is called the Siemens nuclear splitting. When we are passing the radio waves, the lower energy nuclei absorb the radio waves and go to the higher energy state. When we stop the radio waves, it is coming back. When it's coming back, it releases the small amount of energy. That energy, we are sensing it, that we will Fourier transform it, we will get the NMR spectrum. This is the principle you people know. So just I'm touching these things. The next, what are the nuclear NMR active? Any nuclei having odd atomic number or odd mass number, all are NMR active. If it is even numbers, that is also NMR active. Spin should not be zero. If spin is equal to zero, it's not NMR active. Next, sample preparation. You can synthesize very excellent compounds, but if you are not preparing the good sample, you will get the bad NMR spectrum. Okay, the sample preparation is the most important. When you are preparing the sample, so for proton NMR, you have to take the minimum sample. 2 to 10 mg is more than enough. If you are taking the maximum, it will affect the shimming. You'll get the like these kind of broader signals. You won't get the sharper signals. So that's why sample preparation is the most important. For proton NMR, we need to take 2 to 10 milligram. The higher concentration will lead for line broadening. Next, for C13 NMR, we need a higher concentration. Shimming will not affect for C13 experiments and all. For high molecular weight samples, we need a more concentrated sample. Sample must be prepared with deuterated solvents. The deuterium can be used for field locking. Locking and all I will tell you later on when I am explaining that working principle. That time I will tell the what is locking, what is shimming. We are using the deuterated solvents for two reasons. One is for locking and another is for signal swamping. If, signal swamping means if we are using the normal solvent, your compound also having the hydrogen, the solvent also having the hydrogen, the solvent signal will mask your compound signal. That is the reasons we are using deuterated solvent. This is the one of the reason. And another one is for locking. I'll explain you later on what is locking. Next one is the sample NMR tube selection. This is the most important thing. You have to use the proper NMR tube. Some people having that 500 megahertz instrument, they are using the 200 megahertz NMR tube or 300 megahertz NMR tube. This will also affect your spectral quality. When you are looking for the NMR tube, you have to see the two parameters. One is for the OD. OD means outer diameter, and the second one is the Gamber tolerance. These are the two parameters we have to see. Always we have to choose the higher Gamber tolerance NMR tube. So these NMR tubes are made by normal borosilicate glass. For regular experiments, we can use this borosilicate glass NMR tube. For boron NMR, we have to use quartz NMR tube or Teflon NMR tubes also available. Always we have to choose the thin-walled NMR tube, because this thin-walled, if you are choosing the thicker NMR tube, it has a boron and other quadrupolar nuclei, it will affect the shimming. So finally, we will get the bad shimming and will not get the high-quality NMR spectrum. So always we have to choose the thin-walled NMR tube. This Gamber tolerance, that is the, it means how the tube is straight, perfect. So if it is not perfect, then it will affect the shimming. Then also it will be a problem. So always we have to choose the higher Gamber tolerance NMR tube. Next one is the NMR tube cleaning. That NMR tube we have to clean properly. For NMR tube cleaning, we have to use water and organic solvents, finally rinse with acetone. We should not use the brush for NMR tube cleaning. If you are using the brush, then it will make the scratches inside the NMR tube. It will affect the shimming. For drying, we should not keep it in the oven. If you are keeping it, keep it in the oven. So if you are longer time, if you are keep it, the outer Gamber tolerance will change. It will get poor. Gamber tolerance will get poor. The shape will change. It will affect the shimming. Simple hair dryer is enough. Once you washed, kept it for overnight in the room temperature, all the solvents will evaporate. You can use it for next day. For sample preparation, the sample must be sufficiently soluble in the deuterated solvents. Since the deuterated solvents are very expensive, we should not check in the deuterated solvent for solubility. First, you will check with the normal solvents solubility. Then you can use the deuterated solvents. The solution volume should be 0.5 to 0.6 ml, and the perfect depth is 4.5 to 5 centimeter. Less volume of solution will give bad spectrum because of poor shimming. Commonly used NMR solvents are chloroform, CDCl3, DMSO D6, D2O, deuterated acetonitrile, acetone D6, benzene D6, toluene D8, THF D8. These are the common NMR solvents. In CDCl3 molecule has only one deuterium atom, so the deuterium signal search at start of the NMR experiments may fail for very concentrated samples. So that's why we should not use that time lock will fail. So if you are adding the more solvent, then lock will work because of less deuterium. If some of the samples are not properly soluble, we have to filter out and we have to use the clear solution for NMR experiments. When you are using mixture of two different solvents for sample preparation, it is difficult to the NMR instrument for locking the solvent. If you are using mixture of DMSO D6 and CDCl3 as a solvent, you are locking as an DMSO, but the machine picks the CDCl3 signal. Results, every signals will be shifted into the DMSO range. Instead of DMSO CDCl3 mixture, we can use DMSO CCl4 because CCl4 not containing the any deuterium, any hydrogen. So the shift will not happen. So we can easily use this kind of mixtures. Instead of other deuterium, I mean other non-protic solvents, we can use CS2 also we can use. But if we want to use the mixture of solvents. Single deuterated solvent is recommended for good proton NMR spectra. When we are preparing the NMR sample, our hands should be clean because our dirty hands make dirty NMR tubes and it will make the dirty instrument results get poorer resolution NMR spectrum. After preparing the solution, the NMR tube will wipe with the acetone tissue paper, acetone, and clean the NMR tube. Gently place the NMR tube inside the spinner tube and we have to measure the measuring cage with the proper height. If you are keeping too high, like if you are keeping too much height, your solution should not fill the homogeneous magnetic field. It will affect the shimming, will not get the proper NMR spectrum. If you are keeping too much down, it will go and hit the probe and NMR tube will break. So we have to measure the height properly. This is called the depth gauge or a measuring gauge. So this is called the spinners, sample spinners. This is the solution. If you are preparing the less volume of solution, so your solution should not fill the homogeneous magnetic field and the deuterium also not sufficient for locking. So a lock fail will happen. So always we have to prepare the 0.5 ml solution. If you are making higher volume, then it will be fine, but deuterated solvents are very expensive. Next, I am moving on to the working principle. Once we prepared the sample, we put it in the spinner, we kept in the instrument. Once we kept with the airflow, it will reach the probe. Once it reached the probe, the very first step is sample spinning. There is spinning, a mechanical spinning. Okay, the spinning will average out the homogeneous magnetic field. This will lead for sharper NMR spectral lines. Spinning will increase the signal to noise ratio. When we are spinning too much, we'll get the spinning sidebands. Why? Because when it's spinning inside the magnet, the Gamber tolerance always it's not the maximum higher value. Small NMR tube wobbling will be there. It will generate the secondary magnetic field that will give the spinning sidebands. The optimized spin rate is 20 Hertz. See, this is the example of with spinning and without spinning. See here, this is a non-spinning NMR spectrum. Here, the signal intensity is too low. When we are spinning, the signal intensity will be more. We can see the small spinning sidebands. Some people, their concentration will be very low. They'll increase. They will interpret the spinning sidebands also. Because these are the spinning sidebands, they have to know that is not from their compound. This is the artifacts. They have to avoid these signals. Next, once spinning is done, next one is the frequency tuning and matching. So for that, when the NMR experiments are performed for any nucleus, we have to tune the exact frequency. Otherwise, we'll not get NMR signal. Tuning and matching optimize the efficiency of the radio frequency pulses and maximize the sensitivity. For example, in 500 megahertz NMR, if you want to do the proton, we have to give the exactly 500 megahertz radio frequency. If we are giving the other frequency, we won't get the NMR signals. How we are calculating this? This is called the Larmor frequency or resonating frequency. How we are calculating? This is the formula. The Larmor frequency is related to the external magnetic field strength multiplied by the gyromagnetic ratio of particular nuclei. Omega equal to B naught gamma. Here omega is the Larmor frequency or resonating frequency. B naught is the main magnetic field strength. Gamma is the gyromagnetic ratio. These are the this is the table. This gamma is the constant for every nucleus. This is the intrinsic property of individual nucleus. B naught we can change. When we are increasing the B naught, the instrument frequency will increase. Generally, the magnetic fields are measured in the Tesla. 1 Tesla equal to 10,000 Gauss. For example, in 500 megahertz, magnetic field strength is 500 divided by 42.58. This is the gyromagnetic ratio of proton, the 11.742 Tesla. This is the 500 megahertz magnetic field strength. Like we can calculate the any instruments magnetic field we can calculate. In every instruments, for all the experiments, we are not using the same frequency. That is the ATMA. Here I explained. So individual nucleus, we have to change the frequency. That is called the tuning and matching. Okay. So for example, 500 megahertz. If you want to do proton, we have to tune the frequency at 500 megahertz. If you want to do the carbon, we have to tune the frequency at 125.4. Like it's each and individual nuclei, we have to change the frequency. That is called the ATMA or wobbling. Once wobbling is over, then we have to do the field locking. The locking will improve the spectral resolution, reduce the line broadening, leading for sharper signal, and we will get the well-resolved spectrum. Enhance the reproducibility. The locking will enhance the reproducibility. If we are doing the longer experiment, we will get the stable spectrum. Field lock is essential for high-quality NMR data. Okay, what is locking means? The magnetic field is very high. Already I told if it reverses a 500 megahertz, the field strength is 11.742 Tesla. 1 Tesla equal to 10,000 Gauss. Already I told the longer time ppm level, the magnetic field drift will be there. It may be higher or lower. If we haven't locked, so when we are doing the proton NMR, we'll get the broader signals, because the field drift always will be there. Small drift will be there. For the drift adjustment, these lock coils are there. When the field is coming down, this lock coils will give the additional magnetic field. It will make it constant. When the field is going higher, the same lock coils will reduce the, it acts as a resistor. It will reduce the magnetic field. It will make it constant. That is called the field locking. This field locking purpose, the instrument is taking the deuterium as the reference, because we are using the deuterated solvent. This deuterium reference is taking, and it is making the constant magnetic field. That is called the locking. Next, once locking is done, the next one is the shimming. Shimming is nothing. Shimming is making homogeneous magnetic field in whole volume of your solution. Because you prepare the solution, always your solution, if you are taking in NMR tube, compared to the top portion, the bottom portion has the more number of molecules. Okay, the effect, because the outer magnetic field is we have already locked. The NMR tube, if you are taking in NMR tube, in the bottom portion has the more number of molecules than the top portion. The outer magnetic field is constant. The effective magnetic field of individual nucleus is varying. Okay, so for in that case, if it is we are not doing the shimming, the top portion will give the one signal and bottom portion will give the another signal. This is a very close. Finally we will get the shoulder kind of signals. So we want to avoid these things. That's why we are doing shimming. So this shimming, what it's doing, so it will make the homogeneous magnetic field in whole volume of your solution. In top portion, whatever the molecule is there, it feels the same effective magnetic field, and the bottom portion also feels the same effective magnetic field. It will adjust both the things. Then finally we will get the sharper signal. The shim coils generates very specific magnetic field gradient to correct for imperfection in the primary magnetic field. Shimming will minimize the line broadening and maximize the peak resolution. When we are changing the sample, we have to do the shimming. When we are changing the solvent, we have to do the shimming. When we are changing the temperature, variable temperature experiments, that time also we have to do the shimming. Then only we will get the sharper and high resolution NMR spectrum. Once shimming is done, sorry, these are the factors affect the shimming. First one is the solubility. If we are sample as the poor solubility, some solid particles are there, it will affect the shimming. Liquid height, actually your solution, you have to take the proper height. If you are not taking the proper volume of the solution, it will affect the shimming. If solid particles are present in your sample, that will also affect the shimming. Viscosity, if your solution is the more viscous, that will also affect the shimming. Radical paramagnetic impurities are there, that will also affect the shimming. If your solution has the salt of some of the compounds, then that time also it will affect the shimming. Concentration, already I told, for proton NMR, if you are taking more concentration, you will get the bad shimming, you will get the broader signals. NMR tube dimension and cleanliness, this will also affect the shimming. Once shimming is done, then we have to give the radio frequency pulses. When this then we have to start the acquisition. Before starting the acquisition, we have to check the following things. One is for the pulse sequence. What are the experiments we want to do? We have to choose the proper pulse sequence. Next one is the acquisition time. We have to give the proper acquisition time. If you are not giving the proper acquisition time, we will not get the NMR signal. Once we have to give the proper acquisition time, then we have to choose the spectral width, proper spectral width, because sometimes we are getting in that negative region or positive region apart from that general spectral width. So that time we have to increase the spectral width. So we have to choose the proper spectral width. This acquisition time, I told you, that is related to the total data points. If you are giving the more acquisition time, we will get the close data points. I mean TD, total data points. So it will take a lot of time, but we will get the high quality NMR spectrum. Next one is the relaxation delay. So we have to choose the proper. We have to give the proper relaxation delay. For example, your compound is a paramagnetic, the delay will be very fast. That time we have to give the shorter delay. Some of the compounds have the longer delay. So that time we have to give the proper delay time. Otherwise, it will not relax completely. We won't get NMR signal. So that's why the D1 also most important. Next one is the number of scans. So if your sample concentration is too low, we have to give the more number of scans. That also we have to set. Once all the parameters are set, then we have to adjust the gain. When the signal, the gain, what it's doing actually, when the signal is too weak, the receiver gain is increased to amplify the signal intensity. Otherwise, when the signal intensity is too strong, the receiver gain is reduced to prevent the signal distortion. Okay. Once receiver gain is given, then we have to start the acquisition. Once started the acquisition, we'll get the FID, pre-induction decay. This pre-induction decay, once we'll Fourier transform it, we'll get the NMR spectrum. This FID, pre-induction decay, is the frequency domain signal. So once Fourier transform it, we'll get the frequency domain signal. The FID is the time domain signal, and once Fourier transform it, we'll get the NMR signal. Okay, thank you.
Thank you, Dr. Bhaskar, for a nice presentation. And audience, you can ask some query if you have.
Yes, ma'am.
Yeah.
Hello.
Yeah, I can hear you. Tell me, sir.
Which material are the NMR board? Sir.
Yeah, I can hear you, sir. Tell me, sir. Hello.
Sir, hello.
Yeah, I can hear you. You can ask. Hello.
Hello.
Yeah, I can hear you, sir, but I didn't hear your questions.
Which material are NMR board?
Sorry?
Which material are NMR board? One more question, sir. Explain the RF coil. And
yes, sir. RF coil is radio frequency coil.
Or sir, difference between outer RF coil and inner RF coil.
Yes, sir. That is depends on the probe. Okay. In generally, the outer coils are inner coils are close to your sample, it has a more sensitivity. Okay, the outer one is the little bit far, not too far, little bit far compared to the inner one. Okay, so the broadband observed probe X nucleus, because in general the proton is very highly sensitive. Okay, so for when you need a high resolution proton NMR spectrum like NOE, I mean biomolecules, proteins and all, we have to choose the broadband inverse probe that is suitable for who are the people working in the biomolecules and all. For general people, we need a proton also we need, and carbon and other nucleus also we need. For that purpose, this BBO probe is suitable.
Sir, one more question.
Yeah, yes.
Hello.
Yeah, I can hear you, sir.
How is NMR used in medicine and MRI?
So, I don't understand. Sorry, MRI?
Sir, how is NMR used in medicine?
Medifield.
Medicine, sir.
Medical field,
Medicine.
are you saying that now? I think he is asking about the MRI.
MRI.
MRI also, it follows the same principle. There we are getting the imaging. Actually, in MRI, we are detecting the water movements. Water has a hydrogen. We are recording only the proton NMR. We can get the image form. Exactly how is the water is moving. Based on that, we are getting the image. Okay, if water molecule is not there in the compound, we cannot record the MRI, because our body also having the 70% of water. So that's why we are MRI is working for human beings. If it is water molecules are not there, so MRI will not help you.
Here I have one question.
Yes,
regarding the proton as well as C13 spectra. Sometimes people do the same experiment with same sample, same NMR tube. They fill and means 10-15 grams simultaneously and says that continue, please continue our data with same sample. So for recording good spectra, we should make separate sample for NMR or as well as for proton or C13, or we can continue with one sample.
Sometimes if we want to save that time, you have to prepare the separate samples, ma'am. Because for C13, if you are giving 1000 scan, and proton, if you are giving 16 scan, this is enough. If you are taking the proton sample, that is enough for C13 also. If you don't have time for 1000 scans, you want to save the timing, that case, you have to add extra sample for C13 experiments.
But if we are not getting signal, so we should prepare again sample na, for C13.
Yes.
Okay.
Hello,
and yeah, okay.
Sorry, ma'am. You can ask first of all.
You can continue.
Hello, good morning, sir. It was a nice session. My name is Amit Kumar and I am from Patna Science College, Patna University. My question is to you is that what is the use of this in environmental science field?
Material science.
Environmental science field, sir. How can I use it in environmental science field, sir?
Environmental sciences.
Yeah, sir.
Environmental
so how
sciences.
can I use it in how can I use it in this field?
I'll tell. Can you explain more about your research area? Environmental
science. I'm not a research scholar, sir, but I am thinking about it, and I will join it very soon. But in air pollution field and other pollution,
it has a lot of applications. So that's why I'm asking exactly what you are asking. Then we can do the things.
Sir, in the field of like air pollution and water pollution, or
water pollution.
Leachate,
water pollution.
Leachate, which is coming out from the solid waste, sir.
Yeah, in water pollution, we can do the NMR experiments. What are the pollutants are there? For that, actually, we have to choose the water suppression NMR technique. Because in generally, the water signals will be more. So if you are doing the water suppression test, so the water signal will suppress, and what are the impurities are there? That impurity profile we can find out through NMR.
So it will reduce our time hour?
Sorry?
it will reduce our time as well as precise result it will be provide us?
Sorry, I can't hear you properly.
Sir, I am asking, sir,
Yeah,
it will provide us precise result or reduce our time?
Yeah, it won't take this water suppression test won't take much time. That's what you are asking,
sir,
you know?
Thank you, sir. Yeah,
No. Yeah. What are the impurities are there? Those are the things we can find out through NMR. And if you have a metabolites, so we can find out the metabolic profile and everything.
Thank you, sir.
Yeah, thank you.
Sir, I have a question.
Yes, sir.
Sir, in one of your slides, you have mentioned not to heat the NMR tubes and rather just drying them with the air dryer will do the work. But most of the time, we used to get the acetone peak in the NMR spectrum if we do not dry the NMR
Yes, sir.
tubes
In
properly. So,
2.05, always we used to get the acetone signal. That's what you are telling, you know?
yeah. So, is it for some specific NMR tubes, or rather for in general we should not keep the NMR tubes at high temperatures because we generally used to dry.
In general, any NMR tubes we should not keep it in the oven, sir. If acetone signals are coming, we'll keep extra some time for drying.
Sorry.
No, you'll keep some extra time for drying. You'll keep
Extra time
1 day or 24 hours for air drying. Otherwise,
air
you
drying.
can purge the nitrogen.
Okay.
If you are keep it in the oven, so the NMR tube shape will change. That slowly it will change it. Now it will not change immediately. Keep on you are keeping in the oven. So the small changes will be that it will affect the shimming.
Oh, okay. Thank you, sir.
Yeah.
Okay, any other question from audience side? You can ask.
If we have a mixture and all, we can do the dosy diffusion under spectroscopy. Nowadays, many people are doing this dosy experiments. So we can find out the impurity profile, and apart from that, we can find out how many compounds. If you have a mixture, how many compounds are there? Those are the things also we can find out through the diffusion experiments. When the diffusion coefficient is changing, we'll get the separate bands for different compounds. The first slide I showed this dosy, the diffusion measurements. If you have a mixture also, we can record. Now, particularly this is for inorganic people. If they are making the metal complexes, the complex is formed or impurities are there, because TLC also won't work. So in that case, if they are doing the dosy, so we can find out how many parts are there. If it's a single compound or mixture is there.
Dr. Bhaskar, related to dosy, I have one question. How we decide 3-4 parameters for doing dosy in easy way? Because we have a geol NMR machine, and the dosy experiment will take so much time. And
no, ma'am, it will not take much time, because it will take 16 or 24 slices. That is fine.
Okay, but what parameters particularly we should play?
We have to optimize for this gradient strength, ma'am. First, we have to run with 5% gradient.
Okay.
Then we have to do the same experiments with 95% gradient. When the peaks are suppressed, we have to change the P30. In Bruker, we are changing the P30.
Okay.
So if it is not suppressed, we have to change the P30. We have to increase the P30 power. If we are increasing the power, that 95% it will be completely suppressed. Okay. Then we have to start the 2D experiments.
Yeah.
Good afternoon, sir. I have one question.
Yes.
Sir, NMR instrument is available in IIT Patna?
Yeah, NMR instrument is available in IIT Patna. Actually, IIT Patna have two NMR instrument. One NMR instrument 500 megahertz NMR Geol make. It is available in SAIF IIT Patna, SAIF facility, sophisticated instrumentation facility. And another one 400 megahertz Bruker make NMR instrument. It is available in Department of Chemistry of IIT Patna. You are from where?
Ma'am, I'm from Central University, Jharkhand.
Okay.
Department of Chemistry.
Department of Chemistry and SAIF facility. SAIF is a short form and full form is Sophisticated Analytical Instrumentation Facility. You can see our website on IIT Patna website. It is linked with that. Okay.
Thank you, ma'am.
Okay, welcome. Any other question from audience side? Okay, we can conclude the session. And Dr. Bhaskar, thank you very much for a nice presentation, very nice presentation, and it is also fruitful for me.
Thank you, ma'am. Thanks for your nice coordination.
Yeah, because I'm not aware so many instrumentation part, but from today presentation, I got something.
Thank you, ma'am.
Okay, thanks a lot.
Yeah, thank you.
Okay, now close the meeting.
Yes, ma'am.
Okay.